All right, so let's see what that comes out to be. 29.25 divided by 65.44. Well, there's four significant figures, so like 0.4470 mole. And then the prefix milli means 1,000th. So it turns out there's 1,000 milliliters in a liter. Should actually be a capital L, ML to L. Yeah. Oh, sorry. Yeah. Snap. So it's 7 less. Sorry about that. 58.44. I don't know why I wrote 29 there. Like I looked at 22. I mean, I wrote 29 instead of 22. 22.99. So uh, 35 and 35 and 23 is 58. Sorry about that. 58.44. Let's see. There we go. Like that better? All right, about a half mole. 0.505 moles. 58.44. So then if there's 1,000 milliliters in a liter, then if you have 50 milliliters, the conversion factor value in the numerator and denominator have to be equal to each other. So we put 1,000 milliliters in the denominator, 1 liter in the numerator. Because we define a liter or define a milliliter to be 1,000th of a liter, there's no issues with significant figures in terms of the conversion factor. Because the 50 milliliters has three significant figures, in other words, we've measured a volume to within a tenth of a milliliter, it's appropriate to express the answer with three significant figures. That's 0.0500 liters. There's a reason why you need to be able to quickly convert into numbers of moles. And those numbers of moles could come from a mass converting into moles if it's a solid or a liquid. It could also be a number of moles from the ideal gas law. So maybe you know a pressure and a volume and a temperature of a gas. Use PV equals nRT, get a number of moles. In the laboratory, all of our graduated cylinders measure in milliliters. They're marked in milliliters. But you know that when we did work with gases, we use standard volumes in liters. And there's a new thing that you're going to learn about today about solution concentration. And those solution concentration standards are always based upon volumes in liters, liters of liquid. So a liter is the base unit for measuring volume or for describing volume, but oftentimes we measure volume in the milliliter. So it's not unusual to have to convert between units. In other science fields, we use other volumes altogether. What's common in physical science, like geology or physics or astronomy, is to measure volumes in cubic meters. There's 1,000 liters in a cubic meter. So other volume units are used in other types of fields for other different sorts of reasons. Okay, so that's just like a quick review getting from uh, grams to moles and moles to liters. Now you might notice here that it's about a half a mole and about 0.05 liters. So that's going to bring up a problem. If we were to take this mass of sodium chloride, which is just regular table salt, and maybe dissolve that in some water, So we've got 0.050 liters of water. We can describe mathematically how much of the solid gets dissolved in a liquid. So in this world we live in, there are solutions all around us. The word solution has a couple different meanings in English. Like, usually think of a solution as being like the answer to something. You get a solution in a mathematics class or something like that. But the word solution in chemistry doesn't mean like an answer to something. A solution occurs anytime you've got multiple things, not just mixed together, but in one phase, uh, all together. So either a solid dissolved in a liquid, it could be a gas dissolved in a liquid, it could be a gas dissolved in a solid, it could be a solid dissolved in a solid. So, for instance, the air in this room is a solution. The major part of air is nitrogen, but there's also oxygen, carbon dioxide, water vapor, argon, all kinds of gases. So, in that case, for air, we would say the air in this room has multiple parts. There's the solutes. Solute are the things that are in smaller amounts within the solution. It's the stuff that's dissolved. The solvent is the thing that's in the bigger quantity. So this room, the solvent is nitrogen, because nitrogen gas makes up the largest proportion of the air that you're breathing. But there are multiple solutes. There's oxygen, there's water vapor, there's carbon dioxide, there are some other small quantities of other gases, but those are the three major other gases that are in the air you breathe. The oxygen is a really important part, you know? You're breathing out carbon dioxide, and there's water vapor. So if it's really humid, the water vapor concentration is high, carbon dioxide is low. There's always only one solvent, but there can be multiple solutes. The ocean. So we have a whole course, oceanography. You can take it. We do a whole unit just on uh, the solution of the ocean. The major part of the ocean, that's water. That's no surprise. But the ocean's got a heck of a lot of salt in it. If you've ever been to the ocean, been to the shore, it might be surprising to you the first time you get like a little taste of that salt water. You're like, that's a lot of salt. It's not just a little salty, it's a lot of salty. So in the ocean, there's sodium chloride, but there actually is individual ions. There's also gases dissolved in the water. You know, there's got to be oxygen, there's got to be carbon dioxide. Oxygen so that, you know, fish can take oxygen in through their gills. They put carbon dioxide in the water. But the water itself is the biggest part. If you have like Kool-Aid, the solvent, water. And then what do you got in there? Well, there's sugar. Now the sugar is, it's not exactly a solution, but it's kind of close enough. You have some artificial coloring. You have some kind of flavor. But what's always true is that that's a V, Flavor. There's always one solvent. It's the thing that's in the biggest quantity, and then there's a solute. Other things that are solutions like alloys, um, so like gold and silver are way too soft to use as jewelry as pure metals. It's just impractical. If someone ever says, "Hey, I've got this necklace. It is solid gold and gold only," they're lying to you because 24 karat gold is way too soft. You just grab it and rip it right off and break. A gold ring, you'd be able to like squeeze it all day long like Play-Doh would break apart. Same with silver. So like uh, sterling silver is 92.5% silver, and then at 7.5%, well, other filler metals, commonly copper, could be other things because there's other types of silver, but other things. Same with gold. So it turns out if you have 14 karat gold, it's 14/25 or 14/24 gold, and then the remaining portion, the other 10/24 portion, is silver or some other kind of metal because different colors of gold. You know, gold could be white gold or gold colored gold and whatnot. So here's the thing. When you make solutions, you can put different amounts of stuff in that solution. So the ocean has a certain amount of sodium chloride relative to the water. But you can put a little bit of salt in water, make it a little bit salty. You can also take ocean water, dump more salt in it. You make it saltier. Same thing with Kool-Aid. You can make Kool-Aid weak with not much sugar. You can also like really dump the sugar in, so there's like that sloppy stuff down on the bottom. It doesn't all dissolve. So there's a limit to how much stuff can dissolve in water. I got to put a little asterisk beside sugar because the sugar doesn't truly dissolve in the water. It doesn't become a solution by definition, a solution, but it's still within the water column. It's more like a suspension. So these two words, solute and solvent, describe the thing that gets dissolved and the thing that does the dissolving. The thing that's in the lower quantity, the thing that's in the bigger quantity. And the proportion of the amount of solute to solvent, we measure that as the concentration. So, for instance, it's the concentration is the amount of substance, the amount of solute dissolved in some amount of solvent. In generic terms, the concentration can be calculated as like an amount of the solute divided by, well, it's the total volume of the solution. It's some kind of ratio. So if you put a lot of solute in a little bit of solution, it's a high concentration. If you put a little bit of solute in a solution, it's a lower concentration. The air you're breathing right now has carbon dioxide in it, and it's totally safe to breathe the air. But if you happen to breathe air that has a very high concentration of carbon dioxide, it can cause asphyxia. It can lower oxygen concentration in your blood, and it can kill you. So it's not necessarily true that the presence of something is necessarily bad. But if it's present in high concentrations, then it can be bad. Similarly, if you're trying to do some kind of chemical process where you're trying to use a solution as a reactant, the greater this amount of solute per volume of solution, the higher the concentration, and then the less of the material you would actually need. So for instance, maybe we're having a reaction where we're going to take like hydrochloric acid, and we write that as AQ because it's hydrogen chloride dissolved in water. Hydrogen chloride is actually a gas dissolved in water, makes HCl. We can react that maybe with like magnesium to make magnesium chloride, MgCl2, plus hydrogen, and then this equation is not balanced. So there's got to be like a 2 out in front of here. But the deal is this hydrochloric acid, you can make the concentration of the solution really high, and then you don't need much liquid to react with the magnesium. On the other hand, the hydrochloric acid solution could be very weak, not much hydrogen chloride dissolved in water, and then you need a greater quantity of the solution to completely react the amount of magnesium. So up until now, we talked about reaction chemistry in terms of HCl, in terms of how many moles of HCl. We may have calculated the mass, but I told you all the way along that there's this issue about dealing with solutions, aqueous solutions, and that issue's like right now. So specifically, there are a couple different ways to talk about solution concentrations. The major way is this concept of molarity. And molarity is the number of moles of a solute divided by the total number of liters of the full solution. It includes the solute. So that's a new word. And it, derives from the word molar or moles. And we use the symbol capital M to describe the molarity. And then the unit is moles per liter. So the reason why, kind of like as a bell ringer, had you convert from grams to moles and from milliliters to liters is because the standard for molarity is to take the number of moles of solute and divide it by the liters of solution, which has the unit moles per liter, or we just say molar. So for instance, potassium permanganate, that's the KMnO4, when potassium permanganate is put in a solution, it makes like a pink color. And if you put a little potassium permanganate in the solution, it's a slight pink like on the right. Or if you have a lot of potassium permanganate, it makes like a darker pink color. There you can visually see that the left one has a higher concentration than the right one. But in each case, you could calculate what the concentration is. So for instance, if this happens to be, 500 milliliters or zero point 0.5 liters, if you take how many moles of potassium permanganate are in there divided by zero point 0.5 liters, you get a value for the molarity. And it's a quantitative value that every chemist uses to communicate amounts. So we never say, we would never say, take a liter of hydrochloric acid and react it with some mass of magnesium. It's incomplete to describe that because the concentration of hydrochloric acid could be any kind amount. You can go to Lowe's and buy, or most other hardware stores, not like this class not sponsored by Lowe's, but Lowe's and other hardware stores, and buy concentrated hydrochloric acid. And it's very nasty stuff. It can be used to etch concrete. It can be used as a cleaning agent. And on the side of the bottle, it tells you how to dissolve it in water to get it to the concentration you need for the task you're looking to use it for. But the main reason why it's sold as concentrated hydrochloric acid, in other words, as much acid as you can possibly put in the water, is that it's cheaper to ship and it's cheaper to move. Instead of going to buy like 5 jugs of diluted stuff, you just get 1 jug of the good stuff and then dilute it. There's a lot of cleaning agents that come as concentrated solutions. Then you mix them with some water, get them a little bit more diluted. So, but you can never go the other way. You can never like take the water out. In other words, what if you make Kool-Aid and it's not strong enough, it's kind of weak? You can't take water out of the jug, to make it so it tastes stronger. Your only choice is to put more of the solute in. So that's a practical issue. All right, so here's an example. We're going to take and put a certain number of moles of sodium chloride in water. So like on the bottom of the page, what's the molar concentration of a solution made by dissolving 2.5 moles of sodium chloride in 200 milliliters of water. So molarity, the concentration of molarity is equal to the number of moles of solute divided by the volume of the solution. And this number of moles has to be, of course, in the unit, the mole. There's no other option beside mole. Well, we actually have units like the millimole, micromole, but in this course, it's all just in moles. And the volume has to be in liters. Okay, so if I take and put 2.5 moles of sodium chloride in 200 milliliters of water, the way the math goes is I take the number of moles of the solute. The solute is the thing that gets dissolved. 2.5 moles of sodium chloride. And I'm going to put that in 200 milliliters of water. Actually, 200 milliliters of the whole solution. This 200 milliliters is not the standard unit. We have to be in liters. So it's very, very common that the measurement unit is milliliters because graduated cylinders are often marked in milliliters. You can convert from milliliters to liters by going 1,000 milliliters is a liter. So that's 0.200 liters. I guess well, this only really has one significant figure, the way that it's written, like 200 milliliters. That's fine to only have one significant figure. So if I've got 2.50 moles of sodium chloride in 0.2 liters of solution, you take 2.5 divided by 0.2, which is the same as 2.5, divided by 5, 12.5. So the 12.5 has the unit for the numerator divided by the unit for the denominator. It's straight up 12.5 moles per liter, but we don't write moles per liter. Instead, we write this 12.5 with a capital M. And that capital M means molar. And molar to everybody is understood to be like moles per liter. Yeah, she's not here. She didn't come at all. So it could commonly be, and we're going to do some experiments like this, where it'll say like, hey, you need 200 milliliters of 12 molar sodium chloride. So 12 and a half molar sodium chloride would be a solution where you've got 12 and a half moles for every liter. So this isn't one full liter, but if you were to have a full liter, there would be 12 and a half moles of the solution. So, for instance, like concentrated hydrochloric acid, we write something like this: 12M HCl, 12 molar hydrochloric acid. You didn't work with 12 molar hydrochloric acid. You need to use it in a fume hood. It's a fuming acid. In other words, the gas comes right out, burns the eyes, tears up your throat. You don't want any of the vapors around. But another common concentration is to dilute it down to 6 molar hydrochloric acid. That doesn't fume and it kind of smells a little bit, but it's not so bad. But what we commonly used was like 1 molar HCl. And oftentimes we have like common values. Different acids have different concentrations, but 12 molar is the maximum concentration of HCl that's commonly available and sold. Half dilution is 6, and 1 molar is common. But you may have an experiment where you want the reaction to go more slowly. You know that rates of reaction depend upon the concentration. So sometimes we want the reaction to go slow. And to make the reaction go slow, you intentionally have less solute in the solvent. And maybe we use like 10th molar HCl. So zero point 0.1, zero point 0.1 molar HCl is far less concentrated. It's about 100th the concentration of 12 molar concentrated hydrochloric acid. So from now on, when you see numbers with an M after it, that tells you like what the relative concentration is. I'll show you some other ways to use the formula for molarity here in just a second. So another one, we're going to take 37.3 grams of potassium chloride and put it in 2 liters of water. Because we might be making Gatorade, because that's what Gatorade is. So you might, I don't know if you know, I may have mentioned this before, but Gatorade and sports drinks, they contain potassium chloride. But potassium chloride kind of tastes like crap. So you got to put sugar in it or some other thing to like get rid of that terrible flavor. Whenever you like work out or whenever you sweat, you lose a lot of potassium ions, and muscle cramping and fatigue and headaches are commonly caused by decreased concentration of potassium in your body. So to replace the potassium, Gatorade, Powerade, other sports drinks have potassium chloride. So we're going to actually make a solution of like Gatorade, 37.3 grams of potassium chloride in 0.2 liters of water. So the first thing you can do is for potassium chloride, take the mass of potassium, 39.098 grams per mole. You might have a different mass on your like other periodic table. Chlorine's 35.45. Figure out what the formula mass for potassium chloride is, because we're going to need the formula mass of potassium chloride to convert from grams into number of moles. 39.098 and 35.45. Uh, 74.548. So first off, this 37.3 grams of potassium chloride, you can convert that into moles using the formula mass for potassium chloride, 74.548 grams per mole. So oftentimes, as you work your way through courses, and especially in chemistry and other classes in science, you don't just do one thing, you got to do a bunch of things. You got to be like, well, I got to know a number of moles to be able to figure out the molar concentration. But I've got grams, I got to convert that into moles. But to be able to convert grams into moles, you got to figure out the formula mass. So 37.3 divided by 74.548, it's around a half a mole. So we're going to put 0.503 moles of potassium chloride in 0.2 liters of solution. So again, the molarity is equal to the number of moles of solute divided by the volume of solution. So I've got 0.5003 moles of potassium chloride. And that's going in 0.200 liters of solution. Liters is already the standard unit. We're good to go. So that's 2.5 molar. There's three significant figures in the 0.2, so 2.50, it's 2.50 moles per liter, but always write it as 2.50 molar, and we write it as with the what the solute is. So in other words, you can write 2.50 molar KCl. Everyone who's a chemist knows that if you write 2.50 m KCl, that means that you've got a solution of potassium chloride, and it's assumed that it's in water. You can make solutions of things other than in water, but water is a very universal solvent in chemistry. So like in this course, well, 100% of the solutions in this course are water solutions, but there are organic solutions. There are, like, you could use an organic solvent like benzene to dissolve an organic solute. The math is the same, but you would then just say like what the solute is dissolved in. You'd say like 2.5 molar KCl dissolved in benzene or something. But it's assumed that it's in water. You could also write it as 2.50 molar. And when you write KCl AQ, the AQ subscript means aqueous, and it doesn't just mean that it's dissolved in a solute. It specifically always only means it's dissolved in water. Only solutions of water have an AQ. If it's a if the solute or the solvent is something different, then there'd be a different notation here for what the solvent is, or just a written description of how it goes. All right, so that's how molarity is calculated. The other things you can do with the formula is because molarity is equal to like moles of solute, divided by the volume of solution, I'll just write it like this. Molarity is equal to number of moles of solute. Use the lowercase n for moles, and volume is a capital V. So the molarity is like number of moles divided by the volume. Well, then it also turns out that you can rearrange this algebraic equation so that the number of moles is always equal to the molarity times the volume. And then also volume must equal the number of moles divided by the molarity. So if you happen to know like the molarity of a solution, and you know how much volume you have, multiplying the molarity times the volume gets you a number of moles. And similarly, if you know like how many moles of solute you need and what the molarity of the solution is going to end up with, that tells you the total volume that's necessary. So the equation, like any other algebraic equation, could be arranged in any other kind of way, and that's a way to write it. We have other symbols for molarity, and besides molarity, there's other units. There's a unit of concentration called molality, and there's another unit called titer. And those aren't topics in this course, but if you take AP chemistry, there's all kinds of stuff with solution concentrations and dissolution and stuff like that. Okay, so then there's one more step to all this idea. That's because since you can take a solution and you could add more water to it, you can end up diluting it. So what we often do in chemistry is start out with concentrated solutions and perform dilutions. Dilute them down so that there's less, like a lower molarity, but the same number of moles. So here's a concept about that. So what if I have 1 liter of 3 molar NaCl? What that means is that I have a volume of 1 liter, and 3 moles, 3 molar NaCl means that there's 3 moles of NaCl in 1 liter of solvent, of solution, really. So what if I take that 1 liter volume of 3 molar NaCl and I dump it into a container that already contains 3 liters of just pure water? So if I decide to take this solution, which has some sodium chloride in it, and dump that into pure water, there's 2 changes. Well, there's one thing that doesn't change. The one thing that's still the same is I've still got the same amount of sodium chloride. The amount of sodium chloride hasn't changed. I haven't like made salt disappear or have new salt show up. The quantity of salt is exactly the same. So if I dump this solution into here, I still have like 3 moles of NaCl. But as a result of dumping this solution into pure water, I now have a larger volume. I now have 4 liters of water. So what has changed isn't the quantity of salt, but it's the volume of the whole solution. And as a result of that, the concentration will be less. Now, if you calculate the molarity, it's the same 3 moles of solution, or 3 moles of solute, but now I have 4 liters of solution. And instead of it being 3 molar, it'll now be like 3/4 molar or 0.75 molar. So the way that you make solutions of a lower concentration is not to change the amount of solute, because once the salt's dissolved in the water, you can't remove the salt from the water or remove the water from the salt easily. But what you can do is increase the amount of the water that's present. And in this case, when I start out with the sodium chloride, if these dots represent the amount of sodium chloride and they're spaced out some amount, if I have to draw those same dots but in a bigger solution, they're going to be more spaced out. It's going to be the same amount of solute, but in a larger volume. So because they get more spread out, the concentration has gone down. And the value for the molarity has decreased from 3 to like 0.75. You might also see that the total solution, if it's now 4 liters, it's 4 times as much volume. So the value for the molarity gets divided by 4. So 1/4 of 3 is 0.75. All right, so here's a couple different beakers. It looks like I've got some dots in one. Those represent the solute. And I got some dots in the other that represent a solute. And the number of these blobs, which represent the quantity of solute, is the same number of blobs. But in the solution on the left, there's not much space between them. They're kind of packed in pretty tightly. The one on the right, they're more spaced out. They're not as packed in tightly. So we say, this is like a visual observation, this is a relatively high concentration, and that's a relatively low concentration. Like if you make a solution, so maybe iced tea. If it's too strong, too sweet, you add more water and the particles spread out. If it's not sweet enough, you can add more solute. But what you can't do is take solute out or take water out. I mean, you can take water out of iced tea, just let it sit out and evaporate, but that takes a long time. Like the way we commonly get salt that we put on roads and like for food is done by evaporation. and but it's a time-consuming process. It takes 4 years at the San Francisco Salt Works. Show you how this goes. Show desktop. This isn't like a big tourist attraction in San Francisco because it's kind of nerdy and industrial. But this is the Pacific Ocean, and this is the west coast of California. San Francisco is actually a relatively small city up on the end of this peninsula, and then there's the bay, and the southern part of the bay. See this like red kind of thing going on here? Looks kind of goofy. This used to be a salt marsh, and these are evaporating ponds. The different colors here come about as a result of so what you have is like these levied big ponds. You take ocean water, pump it in, and then the water evaporates off and it leaves you solid salt behind. But the red color are different bacteria, algae, and shrimp species that grow well in different concentrations of salt. But over time, those salt flats, the water evaporates out completely, and you're left with just solid salt. And let's see, find a good picture. Cargill, San Francisco. They manufacture, yeah, like here, that's not so bad. Those are the individual salt ponds. And then as the water evaporates away, you get solid salt, and then they take and they kind of plow it up into piles, and then it dries. And then, yeah, these are pretty cool colors. They can be really super colorful depending upon what algae and bacteria is growing in it. So there's some concentrated salt, and then you just scoop it up, bag it up. You buy salt in the store. That's like where it comes from. That one facility manufactures uh, 500 million tons of salt a year, like a lot of salt. Like all the salt for all the food, for all the roads, and all the industrial processes for the country comes out of there. They're big. This is like, they're huge. Like these are whole city blocks here, you know? It's a good environment for it. So the way that they're making the concentration of salt increase and then getting the salt of the ocean is by letting the water evaporate. But that takes a long time. It takes years to do. Okay, so here's the thing about diluting stuff. Whenever you dilute something, you add more solvent. And when you add more solvent, the amount of solute doesn't change. So calculating the molarity of a solution once you've diluted it, the number of moles of solute is exactly the same. But if you increase the volume of the solution, how many liters of solution, the concentration decreases. So the only thing you can do in dilution is to increase the volume, which makes the concentration go down. And that's commonly why we start with stuff that's concentrated and then you add water and dilute it. It decreases shipping cost. Sometimes in manufacturing, it's the right way to start out with stuff. Um, all the saltwater aquariums, I buy salt. I buy about 2.5 tons of salt a year and then mix it with water and make the salt water for doing water changes. I buy salt by the pallet, like a big pallet, big skid. It takes me about 3 full pallets of salt every year and 50-pound boxes.